Seems like it. Seems like it sounds good. Yes. Oh, yes. So, let's get to the topic at hand for today. The content in this video was streamed live on my Twitch. Be sure to check it out. Also, make sure to subscribe to see future videos. At the end of the last stream, I sort of talked about like neural networks and how I wanted to make one. And we made a little bit of progress on that, but I thought I would try and work on and finish the project on stream. So let me give an example of what I was working on, and then you can probably see where I want to go with it. This is the program that I made, and there's not much you need to really know here, except basically all this code that I wrote has, let's see, what is this? There will be little player objects that are all self-controlled, and these are them. And every frame, they have a max speed variable that starts out either being set between 0 and 1. Or no, between 1 and 2. Sorry. And every frame, they will move on the x-axis anywhere from 1 to whatever their max speed is in pixels. So if their max speed is 5, they'll move anywhere from 1 to 5 pixels. And there's also some stuff for gravity, which isn't really important right now. But point is, randomly they will move between 1 pixel and their max speed worth of pixels. And over time, the ones that have higher max speed should travel further, right? Every 8 seconds, this controller object here is going to order all of the different cubes, because there's all the little squares. There's going to be about 100 of them on the screen at the time, all moving according to their max speeds, and generating a random number, every frame moving X a number of pixels. And then once 8 seconds hits, this thing is going to order all of the squares in a list by how far they traveled. And the ones that traveled the furthest, it will sample the max speeds from those that traveled the furthest, in order to create a new generation of, say, 100 more cubes. And so over time, the cubes should learn that higher max speeds means you get further. And that's exactly what happens. If I run my program right here, you'll see that there are a ton of little cubes. They're overlapping, so it looks kind of weird, but you see they're going to the right, and they get, let's see, I'll put my mouse, they got this far, and now we're on generation 2, but you'll see that because they sampled from those ones that performed better in the last run, they actually got about here this time. And then here's our third generation, and these should get a little bit further, although they might not get too much further. All right, they got about here. And you'll see over time, the cubes start getting faster and faster in general. That was actually really good. But you see, there still are some ones that are going a bit more slow. But in general, they are getting faster and faster each time. We're going to have to program a sort of neural network, but we need a visual for it, because visuals are very nice things to have. Are they not? So, here is our little player cube, and we're going to have him going through a sort of like Mario style level where you can run and jump. He's going to have sensors below him to test if there's a floor, in front of him to test if there's a floor, or in front and below him to test if there's a floor, and in front of him to see if there's a wall. So he has 3 sensors, which means if I then come to this layer, here are the neurons for his 3 sensors. These will either be on or off. So let's say there's ground below him, there is no ground in front of him, and no wall in front of him. From this, you should determine that, yeah, I should jump, because if I don't jump, I'm going to go straight into the hole. What we'll then have is I honestly don't think for something this simple, I think I really should only need 1 layer of neurons. But for the sake of understanding how to do multiple layers, I will do 2 layers. My 2 outputs are, should I go forward and should I jump? So it basically always wants to be going forward, but here it should also determine it should want to jump, right? Then we have all the inputs connecting to our hidden layer, which are the light blue neurons, like so. So there's our network, right? What it's going to do, it is going to take the input values, and at each neuron, it is going to apply a function, and that function looks something like input plus bias times its weight, input plus bias times its weight, input plus bias times its weight. And then once we do all that, for the sake of scaling, because these are 0 to 1 values, you basically want to input into a neuron, for the sake of simplicity, a value between 0 and 1. It doesn't have to be 0 or 1. It can be 0.5 or whatever. So what we'll have to do is run the final answer here through this kind of function. Oh, it's behind my head, isn't it? And it's called a sigmoid function, where this is 0 and this is 1. So the minimum value is 0 and the maximum value is 1. It approaches 1 as you go to positive infinity, approaches 0 as you go to negative infinity, and this is how we'll sort of scale our values to be between 0 and 1 at all points. And then, at the very end, all you have to do is take your final answer, right? So you'll get to the outputs. These outputs will also have weights and biases. And then it'll put it through the sigmoid function, get a value between 0 and 1, and then round it. And I'll keep that drawing there for my own sake in the background so I can refer to it later. Now I have to plug my mouse back in. So now we have a system, right, where you'll have network is the variable. The first array is the neuron. So neuron index. And then for the second, like the second dimension is its weight or its bias. So let's say 0 equals the weight. Here 0 equals weight. 1 is the index for the bias. I shouldn't say equals, but it's just the index. But we need to extrapolate a little further here. Right now, we have neuron index and then weight and bias. We need to add this layer. So you have a network, you have each layer of the network, each layer has a certain number of neurons, and each neuron has a weight and a bias. But it also has 3 weights and biases. So this is where our fourth dimension would come in, which is beautiful. But it doesn't really matter. So neuron, then you want the input, right? That's the terminology we'll be using. So now we just need, I'm making all sorts of errors just trying to brute force this just to make sure it's working. Isn't that beautiful? Okay. And we should get all sorts of numbers popping up here. Yep. And it doesn't really look like any of them are repeating in any sort of sensible way, which means it is creating a different value, not only for each neuron, but for each cube. Beautiful. We're on track. Let's say inputs equals, and then let's say 1, 1, 1 for now, although it's going to be actual things, but this is just temporary. Yes, place meeting tests the collision of the player, the hitbox of the player, and if it's colliding with the hitbox of the ground. Whereas position meeting will take these coordinates and see if these specific coordinates are touching the hitbox of the ground. So one coordinate versus the entire hitbox of the player, but we only want to test one coordinate, which is perfect. So position underscore meeting. So we have our 3 inputs. Let's say, is the player touching the ground? Is there a hole in front of the player? Is there a wall in front of the player? I mean, there's got to be a way to generalize this, but for now I'm just going to do it like very simply, which is we want to take an input and multiply it by its weight. So neuron, now we're getting somewhere. This is the calculation we want to do. Input plus bias times weight, right? Perfect. Neuron output equals, this is where we have to do our scaling. How's the work going? It's going actually pretty swell so far. I'm literally going to code the whole thing and then it won't work. Because I don't have any way to visualize it and there's going to be errors that I won't be able to find. these outputs that we just determined, we are going to set the input array to those values so that we can basically just copy and paste this for loop for the next layer. And this is what I mean by I really should have this for loop in a even further out nested loop. Doesn't write comments in his code. Weeks later, he won't recognize his code. Give it 10 minutes. Yeah, no, I know. I'll get there. I will get there. I promise I do comments. I just do comments at the very end. Commenting in the end is like discovering something and rediscovering it to write about. Okay, fine. Watch. We'll do it now. Is it even doing anything? Not yet. Let me show you what all of our code does so far. Oh, you saw that though. No, we have a timer for every 8 seconds, but it's because we're not done yet. By the end, the inputs variable or the outputs variable, it really wouldn't matter, are equal to values between 1 and 0 that we need to run through our output layer to determine whether or not certain action should be taken. Oh boy. And then there's also going to be other things I have to do, like making sure the player can only jump if he's on the ground. So we just need another, like another one of these. Another one of these. But for the output layer. Which, again, this is bad coding. Don't just copy and paste whole for loops. Because there probably is a better way to do it. Cool. We then say, if go right, then x plus equals move speed. If jump and place meeting, this is how we test to make sure we're on the ground. X, y minus y plus 1, obj underscore ground, then y speed plus equals jump speed. Minus equals jump speed. Don't you love it? Let's see if the cubes do anything now. Oh! Error. Incoming. Yes. Perfect. Also, I don't think I have a test to see if the player can actually move through walls. So I think it'll just phase through walls. But something's happening there. Here's my guess. There's no randomness. All of them move in the same motion. So something has gone wrong, but I forgot the range that they should be going from is actually 1 to -1. Not 0 to 1. Oh! Oh! Wait. We're actually getting some behavior happening here. Okay, so, look! Oh my god, it's working! It's working! Now all we have to do is every few seconds have the computer set, well, and then we have to design better levels for it to learn behavior besides just run and jump. So we need to say, hold on, copy the parameters for each layer of each layer and each neuron and each input, its weight and its body. So who's ready for some for loops? Who's ready for some for loops, baby? Here we go. 4. That's it. I can't. I literally just blanked. I took the word 4 and my brain just immediately was like, you should probably stop here. Because it's already in a for loop. Wait a minute. Oh, this is going to get bad real fast, guys. There we go. Now we're working with some 5D arrays. Look at all those nested loops. That'll be readable in the future. Let's see if we get any errors. Because there's no way I'm checking that manually for errors. All you have to do is wait 8 seconds and then see if it actually resets. Index out of range for this line. I have no clue what could be the issue there. Holy smokes. I. Dot hidden. J. J is the layer number, which lines up. This is an I. Oh, there it is. Please tell me if I run this. No, actually don't. Please don't tell me if I run this. Any second now. I want there to be an error. Oh. That was it. It's always something like that. Oh. It's always something like that. Oh, that was great. That's a good one. That's a good one. Amazing. Amazing. Simply amazing. Oh. I understand why a lot of my code might not be, or not a lot of my code, but rather, this is another thing I forget. Currently, the center, this is a good one. This might actually fix things. The center of my cube is currently set to the top left. All the code that I've written assumes that the center of the cube has been in the center. So how about we do that? And we'll see. Oh! 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 Wait. Wait. Oh! Wait! You saw that? There was one that ran until it hit a gap and then it jumped. Wait. There's also this behavior. That's interesting. It only moves when it's on the ground. Oh, you're getting all sorts of weird behaviors now. Oh my gosh, this is so cool. Look at that. That's so cool. Wait. Okay. Hold on. Calm yourself. Holy cow, dude. Oh, now we're getting stop moving when you reach a ledge. That's interesting. We're not getting the desired behavior yet, but we are getting some interesting ones. Stop moving when you reach a ledge is an interesting one. Oh! Pink's got it over here. He even jumped at the end because there's technically no ground there. They're slowly figuring out that they should be jumping over the hole. Oh! Oh! He's done it! He's done it! It wasn't... the logic was there. Mostly. Oh! That's literally so cool. That's the coolest thing ever. It's so simple. Oh, they've unlearned it. That's so cool. I'll double the generation size if I have to. I'm gonna do it. Nah, I'm gonna quintuple the generation size. This is gonna make my computer lag, isn't it? A little bit. And none of them even did it right, anyways. Oh. Oh! One winner! Literally one. But this time, with any luck, there will be more. One winner out of 500. 3 got it this time! Holy smokes, they're learning! Wait, so that now there might actually be a trend towards it. Oh, shoot. Only one. It is random. That is the thing. And 0. They lost it again. It's just so interesting. 4 winners that time! Out of 500. Nearly 1% of them. 6! We've passed the 1%. Wait. So now they might actually start trending towards that. 7. Oh! Isn't it just... It's kind of mesmerizing. 8. Oh my gosh! Show me 2%. Oh! 32. Okay, wait, now it's actually working. Now it's actually working. 53. There you go. 10% of them. That... They broke through. They actually broke through. Oh! 20% of them. I think one of them learned to stop moving when they hit the wall, but jump, and then once they're above the wall, they keep moving right. Something along those lines, which is a very interesting behavior, but still. All right. Anyways, that's the end of the stream. All right. Bye. You may now leave the Zoom meeting.